Good morning everyone. So this is my next lecture in continuation with the lecture number 10 on PN junction. So in the last lecture what we have discussed about what is PN junction, how PN junction can be formed and how semiconductor materials p-type or n-type of materials can be created. So we have already discussed these things in the last lecture. So now I am going to show you what are the PN diode applications. In the last lecture we have discussed about LEDs and lasers. So in the case of the LEDs and lasers we have to apply these type of semiconductor devices like silicon, germanium, gallium arsenide, aluminum gallium arsenide. We can create LEDs and lasers from those materials. So in the case of the PN diode applications, which are basically photo detectors, we can see in the diagram left side that there is a voltage source which is basically in the reversed biased position, because the diode is here. You can see the diode is here, and the diode has we have discussed that it has a positive polarity and the negative polarity. In the left side I have applied a voltage source here. So the voltage source is in reversed biased, as the negative polarity is connected to the positive of the diode and the positive polarity is connected to the negative of the diode. So this is basically reversed bias condition. So as we have discussed that in the case of the LEDs or in the case of the lasers, we usually apply forward biasing, and in the forward biasing what we will do, we will apply positive voltage source to positive terminal of the diode and negative voltage source to negative terminal of the diode. But in the case of the reverse bias, the opposite is there. So this reversed bias condition mainly apply in the photodetectors. There are numerous types of photodetectors like pin photodetector, avalanche photodetectors. These have other applications like avalanche photodetectors have more gain as compared to pin photodetectors when we see about the signal to noise ratio of the avalanche photodetectors and pin photodetectors. So there will be a gain factor in the case of the avalanche photodetector as compared to the pin photodetector. So in this diagram, in the below diagram we have shown that the p type and the n type of the semiconductors material which is in close contact to each other. And as we have discussed that whenever we provide biasing to PN junction, in fact it is a reverse bias position. So when we are providing biasing, that is negative terminal to p type and positive to n type, obviously there are holes, majority of holes in the p type, and here majority of electrons in the n type. So what will happen, the holes will attracted towards the negative polarity and the electrons will attracted towards the positive polarity. So they get separated from the junction. And there will be less number of electrons in the n type and less number of holes in the p type. So the flow of the current in the case of the reverse biased is in reverse saturation current, that is called as reverse saturation current, which is very less or negligible. So the photodetectors have, the light will fall on the photodetector. This is the light, H nu. The light will fall on the photodetector and the combined electron and hole in the PN junction will get disturbed or will get repelled from each other, and they will move towards the terminals like positive terminal and the negative terminal. So here we have written some points that when the light illuminates the PN junction, the photon energy releases free electrons and holes. So what will happen in the case of the lasers and LED, what we are going to what we have seen, that the positive polarity is connected to positive of the diode and negative to negative of the diode, and there will be recombination of the electrons and holes. So they will recombine with each other and they will produce the light. But on the other hand, in the case of the photodetectors, what will happen, the light will fall on the photodetector, the combinations of holes and electrons get repelled from each other and they will produce electrons and holes. So basically they will produce electrons and holes means they will produce electrical energy or electricity. So they are referred as photoelectrons and photoholes here. The applied voltage separates the photocarriers, attracting electron towards plus and holes towards minus. So as long as the light is on the photodetector, there will be a current flowing in the PN junction. So we can see from the left diagram that there will be a flow of the current which is represented by I of t. So whether it is a forward bias condition or a reverse bias condition, the current will automatically flow, but the current will flow, the current is higher in the case of the forward biasing. Here the electrons and holes get repelled from each other and they will get produced, which is termed as photoelectrons and photoholes, and they will create some electrical energy or current in the PN junction. So next we have the energy band diagram of the PN junction. So here we have the N type of semiconductor in the left side and the P type of semiconductor in the right side. So as we already know that there will be a lower energy level which is called as valence band, and the higher energy level which is called as conduction band. In between, if it is an intrinsic semiconductor, in between it is Fermi level. So Fermi level always lies in between the EC and EV, that is the conduction band and the valence band. But in the case of the energy band diagram, when you take both P and N type of semiconductor, this is only for the case of individually you can say a P type of semiconductor, because in the P type of this semiconductor, what will happen? P type have accepted type of impurities. So what will happen? This is EC, this is EV. When there is accepted type impurity, then the Fermi level lies just above the valence band. In the case of the P type, we have already discussed in the last lectures. But in the case of the N type, if we see, so in the case of the N type, what will happen? The Fermi level lies just below the conduction band. So this is your Fermi level. So when you make close contact of P type and N type of semiconductor, what will happen? So there will be, obviously there will be some energy difference created between the P type and N type. You can see from the diagram that the P type have higher conduction band and valence band as compared to the N type, because obviously the electrons and the holes movement, the holes will transfer to the electrons when you contact both the P and N type of junction, and the electrons will move towards P type. So whenever the electrons will move towards P type, there will be lesser electrons in the conduction band. That's why the energy level of the conduction band in the N side is lesser as compared to the P side. So you can see from here that this is the conduction band for the N side and this is the conduction band for the P side. Similarly, the valence band for the N side is lesser as compared to the valence band of the P side. And when we talk about the Fermi level, in the N side, obviously the Fermi level is just above the conduction band, because we have to make sure that the Fermi level will be in synchronizing towards N and P type. So we have the Fermi level just above the conduction band and we have the Fermi level just below the valence band. This region which you can see here, which is basically the curved region, and the distance between the curved region is basically space charge region, or it is also called as depletion width. So this region is called depletion width. So this space charge region will be created when there will be a tunneling of electrons and holes from P type to N type and N type to P type here. So we can see that the energy band diagram of the PN junction will keeps on having a particular flow of electrons from N side to P side and P side to N side, and that's why it will be created a conduction band just below in the N side, just below the P side, and also the valence band just below the P side. So we have this type of energy band diagram for the PN junction. So we have different type of biasing in the PN junction, we have discussed in the last lecture. So whenever there will be no biasing, there will be no flow of the current. When we provide forward biasing, there will be a flow of current, and when we provide reverse biasing, there will be a lesser amount of flow of current. So at zero bias, we can see that there will be no flow of current and the current will be just zero, because we are not applying any external voltage. So the current is also zero. So simplified energy band diagram, this is an IV characteristic of the tunnel diode at basically zero bias. So zero current on the IV diagram you can see, and all energy states are filled below EF on both sides of the junction. So whatever the electrons and holes, they will be occupied by conduction band and the valence band. So at a small forward voltage, when we apply a small forward voltage, what will happen? There will be a tunneling of electrons and holes. So this is your N side and this is your P side. So whenever, because this is conduction band EC, this is valence band EV, similarly this is EC and this is EV. So what will happen? Here the electrons are very much higher in the case of the N side, and in the case of the P side there is holes. So there will be tunneling of electrons from this side to this side, which we can see from the diagram, that the electrons will move whenever we contact both the P and N side to each other, P and N type of semiconductor to each other. There will be a flow of electron from N side to P side in the case of the forward biasing, because what we are doing in the forward biasing, we are providing positive terminal, positive voltage to P side and negative to N side. So we are providing here negative and we are providing here positive. So when negative is connected with negative, so obviously there will be a repulsion and the electrons will move towards the junction. Similarly, positive is connected to positive, there will be repulsion and holes will move towards the junction. So holes will move towards the valence band and electrons in the conduction band of the N side will move towards the P side. So there will be a tunneling of electrons. So electron in the conduction band of the N region are directly opposite to the empty states in the valence band of the P region. You can see this is the empty area of the P side and this is the filled area of the N side. So electrons will move from here to this empty space. So a finite probability that some electrons tunneling directly into the empty state, resulting in forward tunneling current. So we have this forward tunneling current in the case of the forward biasing. So next, so you can see that the current will be some little amount of current is there because we are applying a small forward voltage. So there will be a change in the current which is shown here. So next we have when we apply higher voltages. So when we apply higher voltages, we have discussed that there will be some built-in voltage or built-in barrier which electron and hole have to cross to make a tunneling from N to P side. So again, this is N side, this is P side. We have electrons here, majority, and here we have holes. So when we apply higher voltage, the electrons will move towards from here to here or from here to here. Both the sides is possible. So whenever we provide higher voltage, when we exceed the voltage to a particular, after a particular level, you can say built-in voltage, it will jump into the P side, and similarly holes will move towards here. So this is a simplified energy band diagram and IV characteristic of the tunnel diode at forward biasing, for which the diffusion current dominates. Basically, no electrons on the N side are directly opposite to the empty states on the P sides. So the tunneling current here is 0 and the normal ideal diffusion current exists in the device. So we don't have this type of transition here from this side to, from N side to P side. In fact, we have a jump of electrons from this side to P side. So we have a increase in the current as we increase the voltage a particular level. So we already discussed about diffusion and drift, which I don't think so. Again, we have to discuss it. So diffusion is basically by its own due to the change in the gradient or the concentration gradient. So here obviously the concentration of the electrons is less and here the concentration of electrons is more. So obviously there will be a flow of electrons from N side to P side. Similarly, here will be the concentration of holes are more as compared to the concentration of holes in the N side. So they will move towards this side. So at reverse bias voltage, what will happen when we provide a reverse biasing? So when we provide a reverse biasing, this is N side, this is P side, this will be connected with positive and this will be connected with negative. So when we provide a reverse biasing, there will be repulsion, means attraction towards the terminal. So the electrons will move towards the positive side and the holes towards the negative side, and there will be no crossing of electrons at the junction. So which we can show here from this diagram, the energy band diagram. And here the Fermi level is not the constant as in the earlier one. which is for both for the P and N type. Here the Fermi level is just below the valence band. This is conduction band, this is conduction band, and this is valence band. So Fermi level is just above the conduction band in the N side and just below the valence band in the P side. So we have negative current, this type of current in the case of the reverse bias. So electrons in the valence band on the P side are directly opposite to the empty states in the conduction band on the N side, we can see, and electrons tunnels directly from the P side to the N side easily. The reverse bias current increases monotonically and rapidly with reverse bias voltage. So as we increase the reverse bias voltage, the electrons, whatever the electron left in the P side, that will cross towards the N side, and which is very less. So we have very less current will be in the case of the reverse bias. So at maximum tunneling, how it will happen? The maximum number of electrons in the N region are opposite to the empty states. This is the empty states in the P side. So this is N, this is P. So the number of electrons will move towards the empty states and maximum tunneling will be done, and maximum reverse saturation current or reverse tunneling current will flow. So this will shown in the diagram as V and I. So this will occur only when we have forward biasing. So whenever there will be forward biasing, there will be a more number of electrons will flow from N type to P type, that will cross the junction. So at decreasing current region, so when we have decreasing current region, less number of electrons will flow. So the forward bias voltage increases. So the number of electrons on the N side, directly opposite states on the P side, decreases. So as they will flow towards the P side, because this is N, this is P, electrons will flow towards the P side, and there will be lesser number of electrons left here. And that's why the decreasing current, there will be a curve that after some time the current will decrease when you increase the voltage. So which is shown with this curve. So hence the tunneling current decreases in this case. So what will happen in the case of the forward bias? We have increase in the current firstly, and then there will be a decrease in the current as the number of electrons will get reduced in the N region as compared to the previous conditions. So whenever there will be a lesser number of electrons, obviously there will be a lesser number of electrons flow towards the empty state, and that's why the current will keeps on decreasing. On the other hand, in the case of the reverse bias, we have the reverse current like this flowing towards the junction, towards the particular PN junction, and this current is very much less. So this tunneling current is very less as compared to this current. So next we have to discuss that what is potential barrier. As we have already discussed that there will be some built-in potential, built-in barrier which electron and holes have to cross to jump from N region to P region, electrons basically. So the electrons in the N region have to climb the potential hill in order to reach the P region. Electrons trying to cross from the N region and to P region, but they will experience some retarding field of the battery, therefore they get repelled. So similarly for holes from P region, so there will be some built-in voltage. We have discussed about the formula last time, VBI, that is KT by E ln ND Na upon Ni square. So where Nd is the donor concentration, Na is the acceptor type of concentration, Ni is the intrinsic concentration. So with this formula, whatever the concentration of the semiconductors are there, if we are taking silicon, if we are taking germanium or gallium arsenide or indium gallium arsenide phosphide, whatever the donor and acceptor concentration of electrons and holes are there, so according to that we fix a built-in voltage or we calculate a built-in voltage. So that built-in voltage have to cross, we have to apply particular or you can say exceeding to that built-in voltage. So electrons trying to cross from the N region to P region, obviously they will suffer a retarding field. So we have to see whether the built-in voltage is applicable to that particular point or not. So potential thus produced are called built-in potential barrier, and the values of potential barrier as for germanium is 0.3 and for silicon is around 0.7 volts. So we have discussed what is built-in voltage. We can calculate built-in voltage with the help of the work function, that is work function in the N region plus work function in the P region. So summation of the work function will give you the value of the built-in voltage, or we can calculate the electron concentration, which is N naught is equivalent to Nc exponential minus of Ec minus Ef by Kt, because in the case of the N type of semiconductor, we have Fermi level just below the conduction band. That's why we have taken it is Ec minus Ef. Next expression we have for electrons in the case of the intrinsic type of, so N naught is equivalent to Ni exponential Ef minus Efi. So we have to take, in the case of the Ec, we have to take it EFI. So similarly, we can find out the work function representing the values difference between the Fermi level and the intrinsic Fermi level. Then we can calculate easily N naught is equivalent to Ni exponential minus of Ef, because we can replace this value in this equation and we can get this particular electron concentration. That's why we can easily find out phi Fn value by taking N naught upon Ni exponential will becomes ln here. So we will get final expression of the work function like this. Similarly, for P naught, for the holes, we can have P naught is equivalent to Na, which is the donor acceptor type of concentration, and we have this type of expression, that is Ni exponential EFI minus Ef upon Kt. Similarly, work function can be defined again as in the case of the N type, similarly as in the case of the P type here. So when you combine all these equations, you will get this expression, that is VBI is equivalent to Kt by E or Kt by Q ln NaNd upon Ni square. This Kt by E having the value 0.0259 at 300 Kelvin. So at a particular absolute temperature 300 Kelvin, we have this value. In numerical problems, we can solve by this. NaNd is the donor and the acceptor type of concentration. Ni is the intrinsic concentration. So this formula will give you the value of the built-in voltage or the built-in potential for the PN junction. So there is a problem. To calculate the built-in voltage barrier in a PN junction, consider a silicon PN junction at T is equivalent to 300 Kelvin with doping concentration Na is given and Nd is given. So by putting the values here, we can easily find out the built-in voltage or the built-in potential barrier for the silicon, which is around coming 0.713. So we have to apply above this voltage to make the transition of electrons from N side to P side. So if we change the doping concentration in the P region of the PN junction such that the doping concentration becomes Na is this 10 to the power 16 and Nd is 10 to the power 15, then the built-in potential becomes 0.635. So as you change the doping concentration, the built-in potential or the built-in potential barrier will get changed, and we require lesser voltage to make a transition from N junction to P junction. So this is all about the PN junction, what is built-in potential and how the biasing will affect the PN junction. In the next lecture, what we are going to see about the space charge width expression and about the Zener diode. Thank you so much.